Welcome to our presentation of the patented efficient V piston engine technology. Thank you for taking the time to attend. First, a little about me. I'm Chris Cook, President and CTO of Efficient V. I have nearly 50 years experience, R&D, and design in motorsports, aviation, robotics, and power generation. IMSA and SCCA team crew chief, Alaska NORAD Systems Facilities Engineer, aerospace manufacturing quality control, automotive and job shop machinist, aircraft mechanic with an inspection authorization. I'm the inventor of U.S. patent 8,375,919, motion translation mechanism. My root cause failure analysis observations in the field led me to my search for increased durability and efficiency of piston engines and creation of Efficient V. All these years of exposure to the common core problems in piston engine operation have brought me to some of the solutions I'll be sharing with you here today. I hope you enjoy. Efficient V is designed to eliminate the limitations inherent in the operation of conventional crank, connecting rod, piston slider geometry. It is a core basis of operation for virtually all piston engines, pumps, and compressors. Benefits include reduced friction, improved power and efficiency, optimized piston dwell, harmonious operation, and the option of compact hybrid power integration. First, let's start by examining the problem. This example is a used crankshaft, connecting rod, and piston from a small single-cylinder engine of conventional arrangement. The geometry of this arrangement inherently produces high friction, piston acceleration, deceleration, stress, and wear, and limits piston dwell, reducing the time for complete, efficient combustion and energy conversion to work, torque. As the piston reciprocates in the cylinder, the angular geometry of the connecting rod thrusts the piston into the cylinder wall, producing the majority of friction present in a conventional piston engine, and is the principal limiting factor for efficient, emissions-compliant service life in most piston engines. On the right side image, note the geometry-induced scoring and wear present on the piston skirt. This slide shows failure of an aircraft cylinder engine due to fretting wear from piston rock. Efficient V essentially eliminates piston rock and the high eccentric forces between the piston and cylinder, dramatically extending the life of cylinders, pistons, and rings, and improving efficiency. FAA certified aircraft piston engines in commercial service are required to have a differential compression test, and for some a borescope inspection every 100 hours of operation, or annually, whichever occurs first, and for privately operated aircraft annually, such is the problem. Overhaul is typically required at 1,400 to 2,000 hours of service or sooner, depending on the engine model and condition. The Efficient V model shown here is but one of the many ways this technology may be implemented. Efficient V may be configured with virtually any cylinder bank angle and as a highly efficient V4 or as a radial of 3 or more cylinders, and it is completely scalable. The slide shows a CAD model of our operable 3D printed model V-twin printed at 1/2 scale. Specifications are on the screen. We shall show additional embodiments and arrangements, including a compact V4, after we spend a few minutes on geometry and operation. This circle diagram is representative of the geometry used in Efficient V. The inner circle is half the diameter of the larger circle. The points on the OD of the inner circle represent the crank pin centers of the planetary crankshaft. The crank pins are 144 degrees apart in this example, which is twice the angle of the cylinder bank angle of 72 degrees. Note that although 72 degrees is used in this example, the cylinder bank angle can be virtually any angle desired for packaging or application needs. Note that when the inner circle is revolved in the outer circle, any point placed on the OD of the smaller circle will describe a perfectly straight line transecting the center of the larger circle. This illustrates the geometry-driven cylinder bore-centric straight line piston reciprocation provided by efficient V and how many cylinder bank angles and numbers of cylinders are possible. This slide shows the component and geometry fundamental relationships. The cylinder bank angle is equal to V. The crank pin angular displacement about the axis of the drive pins is twice the angular displacement of the cylinder bank angle, 2V. The ring gear pitch diameter is equal to the stroke. The pinion's pitch diameter is equal to half the ring gear pitch diameter, half the stroke. The crank pin's radial displacement about the axis of the drive pins equals 1/4 the stroke. By altering the dimensions and maintaining these relationships, a mechanism of virtually any cylinder bank angle and stroke may be produced. This video shows an efficient V model's harmonious operation. This example is a 72-degree bank angle, but the operation is the same for any cylinder bank angle employed. As the pistons reciprocate, the planetary crankshaft describes two orbital paths simultaneously. The crank pins received in the piston elongate journals revolve the crankshaft about the drive pin axis, revolving the pinions, which are engaged with the internal ring gears, which revolves the crankshaft drive pin, engaged with the power output receiving journal, revolving the power output. This V-twin section view illustrates core components and component relationships which may be implemented in many applications. The patent also provides for motor generators integral with the outputs, which are not shown in these models. The outputs would be enlarged and can provide electrical as well as direct mechanical power output. This video shows a section view through one of the cylinders and pistons in operation of a V-twin cylinder block. This example is a 120-degree V, but the relationships in operation is illustrative of any cylinder bank angle employed. The cylinders have a narrowed extension that transects the crankcase and journals a corresponding narrowed elongate element of the pistons. The pistons with elongate cylinder journal elements receive and dynamically journal the crank pins of the compact planetary crankshaft, which is robustly and dynamically supported with the reciprocation force vector directly turning it about its own central axis as the crankshaft synergistically orbits the crankcase, revolving the power output. Pressure lubrication may be provided from ports in the block to corresponding journals in the piston elongate and lubricate the crank pin through drillings in the piston. Elimination of the piston skirt minimizes friction, improves oil return to the crankcase, and allows the cylinder deck height to be minimized. This is one of the examples in which this piston technology may be implemented. The design incorporates an elongate journal element, which is analogous to the function of a main bearing in a conventional piston engine. The reciprocation forces of the adjacent piston are transmitted through the crankshaft and accommodated with maximum efficiency and robustness in the piston and cylinder elongate journals. The design incorporates an oilway to receive pressurized oil from the block gallery, and reciprocation hydrodynamically boosts oil pressure, lubricating the elongate journal and crank pins through ports in the piston elongate. And it may optionally incorporate drillings to cool the piston head. The elongate journaling element may be deleted in many applications, and crank pin journal lubrication provided conventionally through crankshaft drillings for further friction reduction. The planetary cylinder bore centric straight line reciprocation dynamics and elimination of the wrist pin enable a robust, lightweight piston head optimized for efficient low friction sealing and minimal thermal and combustion force distortion, providing maximum efficient emissions compliant service life. This slide is one of the patent drawings with color added, illustrating a low friction, high efficiency V4 configuration. The cylinder elongate elements in this view transecting the crankcase are incorporated in the inner two cylinders only, further reducing friction in operation. The outboard cylinder pistons and crankshaft dynamics are efficiently and dynamically supported by the inboard cylinder components and the outboard drive members. For high stress, high output applications, the outboard cylinders could of course incorporate elongate journaling. Not shown, but covered in the patent, is the optional integration of motor generators in the outputs, which could be especially desirable for advanced auto and truck applications. This slide illustrates a V4 arrangement optimized for minimal friction wherein the two outboard cylinders do not have cylinder elongate journaling of the pistons, but are rather more conventionally supported and lubricated through the crankshaft, which is pressure fed through the output drives drillings, but without the friction losses of conventional main bearings. This internal component exploded view provides another look at the component relationships in motion. Although a 120-degree cylinder bank angle mechanism is illustrated here, any cylinder bank angle is possible. Note that elongate journaling could be deleted for many applications with lubrication provided conventionally through crank drillings fed through the drive outputs. Also note the optional incorporation of roller bearings visible in the right side internal ring gear, which can provide robust, low friction support for the power outputs. Crankshaft balance weights are not shown in these illustrations, but would be incorporated as required for balance of the crankshaft unto itself. Reciprocation mass is balanced through incorporation of balance mass in the power outputs and flywheels as needed. This table lists the results of a Fortune 500 company's friction analysis comparing efficient V with their production engine application, which revealed a 3 to 7% improvement in performance from friction reduction alone. This graph illustrates the improvement in reciprocation dwell, comparing a 3-inch stroke production automobile engine with efficient V of 3-inch stroke. Note that when both are at 90 degrees of rotation, the efficient V piston is mid-stroke, and the conventional example has traveled a further 231 thousandths of an inch down the bore. This slide shows in red the reduction in deck height possible with efficient V. For pushrod applications, reduced deck height enables improvements in the valve train through the use of shorter, lighter push rods and reduced valve spring pressure, which reduces stress and friction. This was a proof of concept Efficient V single-cylinder compressor completed as an Oregon State University Mechanical Engineering senior class capstone project, part of their final exam. They converted a production single-cylinder compressor to Efficient V operation, retaining the original cylinder, piston, and head. This is a photo of the operable 3D printed V-twin mechanism illustrated in component detail views and is available for examination after the presentation. Efficient V has a broad scope of applications and benefits in advancing engine applications, hybrids, power generation, compressors, and pumps. So summing up, Efficient V provides improved dynamics with geometry-driven, cylinder bore-centric, straight-line piston reciprocation, which promises superior cylinder sealing and component life with reduced maintenance and service costs. Efficient V promises significant improvements in efficiency and durability in numerous applications: engines, hybrids, pumps, and compressors, with improved packaging and function. Thank you very much for your time and interest in exploring Efficient V with us. We'd be very pleased to meet with you and answer any questions about Efficient V and how we might be able to collaborate or be of service. If you have any questions, please contact us or visit our website. From Scott and I, wish you all the very best, and thanks again.